So the goal of this project was to create a compact, user adjustable and responsive oscilloscope that takes in 2 voltage measurements and displays them on an external display. A few of the challenges during this project: interfacing the data processing block with the VGA display proved pretty difficult. Oftentimes the VGA display would break if there was too much happening in the code, and so we had to do a lot of adjustments there. And additionally, the 1 megahertz sample rate requirement was a difficulty of ours. We were only able to reach a sample rate of 0.1 megahertz, which is off by a factor of 10. However, a few achievements during this project is the portability and ruggedness of the oscilloscope. The case is compact and you're able to kind of chuck it around. It can survive a drop test, put it in your backpack, take it to the lab, whatever you need to do. The VGA custom GUI is very simple, easy to read, and responsive to user inputs. Additionally, the trigger functionality works quite well, and also the voltage inputs can read up from negative 10 volts to positive 10 volts. A few considerations for the future, if we had more time to work on this project, would be to implement additional trigger functionality, being able to use the trigger on both channels instead of just channel 1, and also being able to detect falling edges as well as rising edges would be nice. Additionally, implementing additional measurement capabilities such as frequency calculations using fast Fourier transform algorithms would be nice. And increasing the sample rate would also be a great consideration for the future.
The overview of the design can be broken into 4 main blocks. It starts with the inputs. We need to be able to take in 2 voltage signals. We need to have a user interface which can take in user inputs, and we also need power for the system. Next, that data needs to go into processing. We need to be able to sample the voltage signals. We need to check for user inputs and also implement the trigger function there. Lastly, that information is going to go into the outputs to some sort of display. It needs to display a voltage and time axes. It needs to display a menu that the user can interact with. And of course, it needs to display the input signals. The last block is the enclosure, which kind of integrates the entire system together. And the idea behind the enclosure is to make something that is portable, so it needs to be able to easily disconnect and connect to external devices such as the monitors and the oscilloscope probes. It needs to be compact and lightweight, but at the same time it also needs to be robust and able to withstand hard impacts.
The system has one main circuit, and this handles the 2 varying system level inputs, these being the voltages that we are measuring and the user input, turning of a knob or pressing of a button. On the voltage measurement side, we have 2 attenuators. These attenuate the voltages that we are measuring down to the voltage specifications of the ADCs on the Arduino. And on the user interface side, the circuit provides voltage to the button and the knob so that when a user makes an input, the Arduino will know that a change in the voltage is made. All this circuitry is all laid out on a PCB so that everything is all in one place and secure. So a quick explanation of the user interface. Since we only have 1 button and 1 knob, the button allows users to switch between adjustment modes, and the knob allows users to adjust the levels of those modes. For example, if the user selected time adjustment mode with the button, turning the knob would scale the time axis displayed on the output display. Also, if the user was in trigger mode, turning the knob would adjust the trigger level. All this information is sent to the Arduino through changing voltage to the Arduino's input pins, where code reads those inputs and processes that information and updates variables accordingly.
So another portion of our project is the data acquisition block. This handles reading in voltage values from the attenuator circuit on the PCB, reads in these voltage values through the ADC pins on the Arduino, and stores them in an array within the program. This was designed to use the Arduino's ADC in free running mode, which allows the program to essentially directly read the ADC registers, which makes the sample rate much higher than using other means. Originally, this block was designed for the DE10 Lite FPGA using digital logic. However, this proved too cumbersome to implement with the Arduino, as we would require some sort of serial communication between Arduino and FPGA, and it made also integrating the VGA display very difficult later on in the project. So we decided to drop it and settle for the lower sample rate on the Arduino, which we managed to get up to 0.1 megahertz. Another portion of our project is the data processing block. The main job this block does is implementing trigger functionality. This trigger uses a form of hysteresis, which compares the current and previous voltage values on channel 1 with the trigger level, which is set by the user adjustable knob. Once the trigger event occurs, then the arrays will be updated with new values. The user can change modes, and then the display will be updated accordingly. Additionally, this block required a lot of work during the integration phase, making sure that the processing and acquisition code was playing nicely with the user interface code and the VGA functions, and making sure that we still had the sample rate and VGA functionality that we designed for.
Once we have the data from the inputs and it's been processed, the last step is to take that data and output it to the VGA display. The inspiration behind the VGA display came from finding a VGA library which is compatible to the Arduino Due, and that allows me to very easily print out pixels and lines and text to the VGA screen. So the first thing I had to do was interface the Arduino with the VGA screen. So I designed a dongle which hooks up to certain pins on the Arduino for color and for syncing, and that connects to a female-to-female VGA port, so that wherever you are, if you have an external VGA compatible monitor, you can easily hook it up to the Arduino and print it out to there. Once I designed that, I need to design the code for the display. First thing I did was create a voltage and time scale which can adjust based on user inputs. I needed to create a menu for the user to be able to see what mode they're on, what modes they're adjusting, and also what the values of each mode are, including the trigger. The last part was, of course, to print out the input signals onto the screen in proportion to what the user has decided the voltage and time scales are. Two major downsides to using the VGA are, one, the resolution is very low, so that prevents us from displaying very sharp images. And secondly, the VGA library is not very efficient, and which in turn causes a very noticeable flicker effect on the screen. Once we had all the inner parts of the system level design working and ready to go, we had to integrate all those parts inside of an enclosure that would protect the system, making it compact, lightweight, portable, but also very sturdy. That was one of the major requirements we wanted to have, was the sturdiness of the system. So we decided what better way to test the sturdiness than to drop it from 3 feet and see if it still works. The inspiration for the enclosure design started with a basic box with a raceway lid. I designed this first prototype in FreeCAD and then designed more and more prototypes, adding on more customized measurements according to the internal components and how they would interface with the outside environment. In order to give this thing more protection for the drop test, I designed custom corner caps for each of the corners of the enclosure out of a more malleable material than the regular plastic. That would give us more cushion when we dropped the system to make sure that it would still work afterwards. I also added magnets to the raceway lid to make sure it didn't fall off, and I also included screw holes in the bottom in very precise locations so that we could secure the PCB, the Arduino, and the enclosure all together. One major downside to the design of the enclosure is that you have to take the raceway lid off in order to interface with the button and the potentiometer. So this leaves the system very exposed to the outside elements when you're using it. So one way to improve upon this would be to make those elements accessible even when the lid is on.
Reiterating on some of the main achievements in this project, we were able to design a very portable, sturdy oscilloscope that's very modular as well. With the VGA output, a user can see outputs displayed on monitors or smaller displays or even projectors, making it extremely versatile. Also, the user interface with just a knob and a button is extremely user-friendly and easy to learn, making it ideal for inexpensive lab kits or even use in high schools where students who are interested in electrical engineering but don't want to be overwhelmed by all the knobs and buttons and functionality of industry-grade oscilloscopes, they will be able to use this very easily as well.